Hi, I'm Sharon.
And I'm Lindsay.
We're in Dr. Zaurin's statics class.
And this is our extra credit problem for 3.14. Okay, so we're going to be explaining how we set this up. The first thing we did is decided that we were going to use 2 green rubber bands for AC, 3 orange rubber bands for AB, and 4 red rubber bands for AD. We did this to try to keep a little bit with the project as their values were 20, 30, and 40. So the next thing we did is we put the rubber bands over here and we did the unstretched lengths of the green, the red, and the orange. They were all pretty much the same, so we decided that this would be a good way to move on with our project. The next thing we did is we needed something to measure our weight with, so we decided to use a bottle of water. We halved the bottle of water, and the first thing we did was use the stretch length with half of the bottle of water. So we filled up the bottle of water with only half, and then we went and recorded the stretch with half full for the green, the orange, and the red. The next thing we did was fill the water bottle up with all the water, so 16.4 fluid ounces, and then we went back and did the stretch length. After that, we're going to do some calculations, and we'll show you those later, but once we put it all together, it made sense. We measured the distance from A to C, and then from A to C here, this distance, and we're going to be using those in our project.
So as in the experiment that you saw before, we used a full water bottle and a half full water bottle to do our spring constant calculations. The first water bottle test we did was a half full one with 8.545 fluid ounces, which turned out to be about 0.250 kilograms. How we accounted for the empty water bottle was by adding 0.01 kilograms to each calculation. In the full water bottle with 16.9 fluid ounces, it turned out to be about 0.499 kilograms. So we took the mass of the water bottles and we multiplied them. We used Hooke's law to calculate the spring constant by rearranging for K. So in this calculation, we had to take the force divided by the stretch, which is mass times gravity divided by the stretch, in order to find the spring constants. As you can see down here, for the green system, which is the system of 2 rubber bands, we had it stretched with full water bottle length of 11.1 centimeters, which turned out to be 1.111 meters. The stretch with half was 8.2 centimeters, which turned out to be 0.082 meters. Then down here, for the spring constants, we used Hooke's law, did the mass of the water bottle system times gravity divided by the stretch length to find the spring constants for K1. For K2, which was the stretch with half system, we did the mass of the half water bottle times gravity divided by the stretch with half water bottle full. We took the average of these 2 spring constants and found the average spring constant to be our final, which was 38.045 newtons per meter. We completed these calculations with both the orange and the red spring system as well. As you can see down here in our free body diagram, we have labeled the complete system with final spring constant KAC being 38 newtons per meter, spring constant spring constant KAB equal to 41 newtons per meter, spring constant KAD being 45 newtons per meter. As Dr. Zaurin mentioned in his YouTube video, the picture in the textbook is drawn incorrectly because the system with the smaller spring constant, being this system, should have the longer length, but in the textbook it's drawn the opposite way. The calculations that we got with the lengths from the horizontal length from A to C turned out to be 0.178 meters. The vertical length from A to C was 0.087 meters. From A to B horizontally was 0.142 meters. And now that we have all the calculations, we can move forward with our project.
So now that we have all of our springs constants we found earlier, plus our free body diagram, we can go ahead and apply Hooke's law to find our stretches. The first thing we did is an FAD, which we found by doing mass times gravity, giving us FAD as 4.993 newtons. We then applied Hooke's law, and that gave us FAD divided by our spring constant we found earlier to equal the stretch. When we did this with our numbers we found earlier, it gave us 0.112 meters for our stretch of AD. The next thing we did is to find FAC and FAB. We used geometry and triangles from our free body diagram. Because they were right angles, we were able to use Pythagorean theorem to find our hypotenuses. We then came over here and did the sum of f of x. So FAB equals our geometry from our triangle minus FAC times our geometry from our triangle equals 0. And then we did the sum of y the same way. We then used that as a system of equations, and we went ahead and we found for our values, which Sharon will explain later.
As Lindsay said before, we set up a system of equations to be able to solve for our individual forces. How we did this was solved by elimination. First, we eliminated the FAC component to find FAB equal to 5.334 newtons. Then we plugged in that value back into equation 1 from before, and we got FAC equal to 5.043 newtons. After that, we were able to plug them back into Hooke's law, solving for the individual stretch of each component. So for the AB component, we got the stretch was 0.129 meters, while the stretch for the FAC component was 0.133 meters. And these small values make sense because our model was on a much smaller scale than the model in the problem.